be a unit circle person, you want to be able to sketch a unit circle pretty quickly, or at any value find the point that you need. Hopefully the X and Y axis are pretty easy, right? Like these points, can you do those without much effort? Or not? Right, it's a radius of 1, so like at 0, what is that point going to be? 1, 0, because the X is 1, like I'm on the X-axis. I'm not moving up or down any, so that's why the Y is 0. And if I go up here and I'm up on the Y-axis, what's that point going to be? Now I'm on 0 on the X, but 1 on the Y, right? Like those are the points that I hope aren't so bad to do. Over here, I'm on the negative side of the X-axis with a radius of 1, so that's negative 1, 0. And down here, I'm on the negative Y, so that's 0, negative 1, right? Hopefully that makes sense. The other ones are the ones that we want to make sense of. And just a reminder, do you know what these values are? What's the smallest angle on my unit circle after 0? Pi 6 is the smallest. The bigger the denominator, the smaller the number, just so you're aware. And what's the angle that cuts right in the middle of the quadrant? Pi 4, 45 degrees. And then the next one is pi 3. I'm not going to go all the way around here. We've done this many times. I don't want to waste the time doing it. But we could keep going, and hopefully we could find all those values. What I want to do is show you, if you make some ordered pairs here, a really quick way that you can make the unit circle. So if you start at the top, at the x coordinate, you can write 1, 2, 3. Yes, but you should know that there's going to be fractions. So start at the top and count down. 1, 2, 3, and then go next to it and count back up. 1, 2, 3. Want to follow me on that? 1, 2, 3. 1, 2, 3. And then put everything over 2. Because we know there's fractions here. And then we're going to go through and take the square root of the top of every number. But what's the square root of 1? So I don't need to put a square root on that. But the square root of 3, I'm going to put a square root sign on it. I'm going to put a square root on top of both of those 2's. Square root. And again, I'm taking the square root of 1, but it's just 1, so I don't have to do it. And guess what? I just did the first quadrant of the unit circle. And it always works. Kind of a little trick. Well, the rest of it, you got to know which ones go together and change the quadrants. If you know quadrant 1, you should be able to do the rest of them. And so I always go in groups. So let's start with the ones that are the same, pi 4. Could you go through and tell me which other angles are going to have these same coordinates but change the signs?
No.
Yeah, all the middle ones. This one's going to be 3 pi 4. This one in the middle is going to be 5 pi 4. And this one down here is going to be 7 pi 4. They're all going to have the same ordered pair as the square root of 2 over 2, square root of 2 over 2. And then you have to make sure that you know the negatives to go with it. So really, if you know the first quadrant, you should be able to do the rest of them. So in quadrant 2, I know it's still square root of 2 over 2, square root of 2 over 2, but which one's negative? Yeah, x is negative, so it's negative square root of 2 over 2. And 5 pi 4, quadrant 3, they're both negative, so it's negative square root of 2 over 2, negative square root of 2 over 2. And 7 pi 4, still the same ordered pair, but which one's negative in quadrant 4? The y. So it's positive square root of 2 over 2, negative square root of 2 over 2. So that's why I say there's a little trick for the first quadrant, and then you can just go from there. You can do the same thing with all these other angles. Pi 6, every angle that's the same reference angle, or right next to the x-axis, is going to be a 6, and then it's going to have the same ordered pair, but just changing the sign. So pi 6, and this one, which is 5 pi 6, it's going to be the same one. You just flip it around. That's where those reference angles are important, to know that those are the same distance away from the x-axis. All the ones that are 1 away, like this distance, which means the one right down here, that's 7 pi 6, and the one right over here, which is 11 pi 6. It's also going to be square root of 3 over 2 1/2, and then you just change the sign. So I think here I'm going to have negative square root of 3 over 2 1/2. And down here I'm going to have negative square root of 3 over 2 negative 1/2. And over here I'm going to have square root of 3 over 2 negative 1/2. And we should only have thirds left, and that's what's really kind of great about the unit circle. If you know your angles, all the fourths go together, all the sixths go together, all the thirds go together. Because all the ones left are pi thirds away from the x-axis. This one up here is 2 pi thirds. This one down here is 4 pi thirds. And this one left right here is 5 pi thirds. And again, they're going to have the same ordered pairs pi thirds, but just changing the sign. So I always say it looks overwhelming at first. Of how in the world could I memorize that whole circle? But if you know the first quadrant and you know reference angles, then you should be able to do this fairly quickly. So this one's going to be negative 1/2 square root of 3 over 2. Should have written that one sideways, but this one's going to be negative 1/2 negative square root of 3 over 2. And then 1/2 negative square root of 3 over 2. And if you know those, and they ask you to find any trig function of any of those angles, you know them by just knowing the point. The x and the y are the cosine and the sine, and you can figure the other ones out from there. But you don't have to. You can be a unit circle person. I watched that trick on a little video on YouTube about the 1, 2, 3 thing, and I've always shown it since then because people seem to like it. But just so you know, you got to know where to start with the 1, right? Like if you start up here with 1 on the outside, then it kind of messes things up. I always think about x and y, like which one's higher or lower. I'm not going to lie. When I'm trying to figure out which one goes with this one, I think about this one is the lower y value and this one is a higher y value if you're thinking about the y-axis. So I always remember 1/2 is smaller than square root of 3 over 2. I'm not a shortcut kind of person, but you know, triangles work too. But I just want to show you that. We're having a test next Monday. You got to either know this or know your triangles really well by then. So it's my last time making me write this unit circle. Some people on the test like to start by making a big giant unit circle. You can do that. I don't recommend it. I say just wait and see what you need. But some people every year, that's the first thing they do is spend about 5 minutes making a big unit circle, and then they can refer to it the whole time. I want to get to the last thing that I want to talk about today is sine and cosine and talking about their domain and range and such. So I just have a couple little slides of notes here. This is our last day of notes before our test. And this kind of goes right with that worksheet, so it kind of worked out well that we did that worksheet yesterday. My pencil sharpener is terrible. If you can try that one or go to Mr. McClure's if it's not working. All right. We're not going to graph these until after we have our test, but we do want to kind of think about the domain and range of these. The domain is what you plug in for theta, maybe, is what you would think about. Like, if I had sine of theta and cosine of theta, the domain would be kind of like the theta part. And although our unit circle, we picked very specific angles, like pi 6 and pi thirds and 2 pi thirds, could I take the sine and cosine of anything? Could I take the sine of 17 degrees? I don't know what it is, but I calculated I could. Could I take the sine of 5 million degrees? Yeah, I could take whatever I want. So if I can put whatever I want in there for theta, what does that mean my domain's going to be? Always all real numbers. So I'm going to write that as negative infinity to infinity. Now the range range is what I get back out of that. And I kind of was leading to that with the bottom part of that worksheet that we went over with the maximum and the minimum value. What was the biggest value that we ever got out of sine and cosine? And what was the smallest value? Which means no matter what angle you can think of, however big or however small, the output or the range will always be in between -1 and 1. We kind of call this a wrapping function, not like wrapping like wrap, but wrapping function in that it just goes around on itself. Like if you think about the unit circle, it's just going to keep going around and 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 around. No matter what angle you think of, it's going to end up somewhere on that unit circle. And so that's why it just repeats itself over and over again. So why is this important? Well, not only are we talking about sine and cosine here, but think about our unit circle. In our unit circle, we know that the x is the cosine and the sine is the y. So we can kind of even throw in this here. That we can say that the y value is going to be in between -1 and 1 for sine. And the same thing for cosine. We could say that the x value is between -1 and 1. But x is cosine, so cosine is always between -1 and 1. And we've been kind of talking about this a lot, but this means, although our unit circle only goes from 0 to 2 pi, we can evaluate any angle, way bigger than 2 pi, way smaller than 2 pi, because we can just figure out where it is on that circle, because they're all going to be on that circle. And so this kind of goes back to the whole coterminal angles, but I have another way of writing it here. We can add any multiple of 2 pi to our sine, and again, they're using t instead of theta. If you like theta better, you can use theta. And they've been throwing lots of big numbers at us, and I've always been saying, well, you can always add pi or subtract 2 pi. But this is kind of just writing it out. If you have any angle and you add any multiple of 2 pi, that's what that n means, any multiple of 2 pi, you're always just going to be at that same value that you originally started with. And the same thing with cosine. And that's because they just repeat themselves over and over again. We call these periodic functions. And all of our trig functions are actually going to be periodic. But right now, we're just talking about sine and cosine. So what does this mean for us today? Well, today they're going to throw some big values at you and ask you to figure out what the value is. And the idea is just figure out what the original angle was. And don't worry about it if it's like 8,000 pi. You don't have to subtract 2 pi a million times. I want to give you an official definition of periodic, and then I'll give you a couple examples, and then I'm done. So I'll be some short notes today. Ready for some math talk? Here you go. Here's math talk. A function is periodic if there exists a positive real number. That's what this R stands for. If you want to change that to a real number, you can. And they're calling that real number C in this formula. And they're saying that if any function is periodic, when you add that positive real number to the original function, it's the same as the original function. And what we care about is what's the smallest number that C could be. And that smallest number that C can be, we call the period of the function. And another way to describe the period is how long it takes for that function to cover the entire values. Like, we know sine and cosine go from -1 to 1. The period is how long does it take to go from -1 to 1. And we should know that already, but it's always kind of funny to talk about the length of the period of sine and cosine. Mr. Mills told a great story one day when he was student teaching. His professor was there watching him, and so he was kind of nervous because his professor was in the back of the room, and he said they'd been doing sine and cosine. It was a really simple problem, and he kept saying, "What is the period of sine?" And no one would say anything, and he's like, I was kind of freaking out, so I was like, "How long is the period of sine?" And no one's saying something, and so finally he's like, "How long is my period?" And then all the kids start laughing, and his professor's in the back of the room. I think about that every time I teach this, because I can imagine Mr. Mullis yelling about his period. No. He was supposed to go back to college in Evansville, but he's still living in Indy, so I don't know what he's doing. Maybe back to college in Indy. You should look him up on Facebook and ask him. Probably. So for sine and cosine, how long does it take to cover all the values? It's around the unit circle one time. So the length of the period of sine and cosine are both 2 pi. And if you want to write that, this is the amount of time to cover all values. Once it goes from 0 to 2 pi, it just repeats itself over and over and over again in that same pattern. So that's why the period is 2 pi. And we've talked about this a lot. You can always just add or subtract 2 pi. But just to kind of remind you, I just kind of gave an example here. Sine of pi is always going to be the same as sine of 3 pi, because how did I get from there to there? I just added 2 pi. And I could add 2 pi again. It's going to be the same as the sine of 5 pi. It's going to be the same as the sine of 700 pi. Sorry, 7 pi, I mean. I could pick a really big number, like, not 700 pi, because it needs to be an odd number, right? 99 pi. Does that work? So I could just keep adding 2. It would all be the odd ones. So today, we've been doing some that aren't too big. Today, they're going to give you some really big numbers. Just remember that you can always keep adding or subtracting 2 pi, or especially if it's an increment on the x or y axis. You should be able to think about every odd number pi is always going to end up on the 180 side, right? The pi side. Every even number pi is going to end up on the 0 side, because if you add 2 pi, 4 pi, 6 pi, 700 pi, 1000 pi. So just remember, it's the same as this, which would be, what would be the value of all these? What is the sine of pi? Or 3 pi, or 5 pi, or 7 pi, or 99 pi? Sine is which coordinate? The y. And what is the y coordinate at pi? 0. That's on the x-axis. So all of those are 0. Questions about that? Again, we'll get back to more of the whole period stuff when we get into graphing it, but today that's really all you need to know. One more thing. I think this might even be my last slide. Okay, maybe one more example after this. No. Even and odd functions. We've talked about even and odd functions with polynomial functions. Trig functions are also even or odd. Just a reminder, even functions are symmetric with the y-axis, which means it's the same on either side. The most common even function that we have is y equals x squared, because when you graph that, it's the same on both sides, right? Remember vaguely talking about even functions back first semester? More importantly, how do you know if something's even? Well, if you plug in the negative number, you get the same thing as if you would have plugged in the positive number. So there are 2 even trig functions, and it's cosine and it's reciprocal. So it's really easy to remember. Cosine and the one that goes with cosine Those are the only two even functions, which means if you plug in a negative angle, you get the same thing as the positive angle. So just an example here, if I said the cosine of negative pi 6, I could just graph negative pi 6 or add 2 pi and get the positive angle. But because it's even, I know that that's always going to be the same as the cosine of pi 6, which maybe I should know from my unit circle. Pi 6 is the smallest of the angles, right? And cosine is the x, so that's going to be square root of 3 over 2 1/2, so that would be square root of 3 over 2. And you can do the same thing with secant because they're even. So you don't have to stress about negative angles. If you know it's an even function, you can just make it the positive angle and go from there. But what about the other functions? All the other trig functions are going to be odd functions. The same way, except for what's the ratio, what's secant? It's the reciprocal of cosine, right? So if we did the same one, pi 6, what would be the secant of pi 6? I would just flip this over and then I'd have to simplify it, right? Sorry, here, if we did the secant of negative pi 6, that would be the same as the secant of pi 6. It's just flipping this over, right? Or it's 1 over this, but it's just 2 over the square root of 3. And then obviously you wouldn't leave your answer like that. You can multiply by the square root of 3 on the top and the bottom, and that would be 2 square root of 3 over 3. So if you know sine and cosine, if you know the point, you also know secant and cosecant because you just flip them over. Right? Remember that? You can also draw your triangle. I promise it still works at pi 6. So it'd be 1, 2, square root of 3, and you could use that same way. Odd functions. An example of an odd function that we know is x cubed. And if you think about the graph of x cubed, the positive side goes up, and the negative side is exactly the same, except for it's negative, right? So what does that mean? For an odd function, if it's negative, then the whole answer is going to be negative. So we could say sine is an odd function. So if you see the sine of a negative angle, it's going to be the opposite or the negative of what that positive angle would be. And we'll do some examples of that. And not only is sine odd, all the other trig functions are odd. So I always say don't feel like you have to memorize this whole thing. Know which ones are even. There's only 2, cosine and its reciprocal. And then if you remember cosine is even and all the rest of them are odd, then you don't have to worry about memorizing all of those. But sine and cosecant and tangent and cotangent are all odd functions, which means if you take the value of one of those negative angles, you're going to get a negative number out of it. And we're going to do an example of this. And again, do you have to use this? No, because you can always just add or subtract 2 pi to get to a positive angle, and it really still works. It's just another way that you can evaluate these. Okay? Everyone trying this? I got 2 examples here. They're on the same page though. Look, it's really short. Oh my gosh, it's not even here. Where's my examples? I'm going to make them up here. Evaluate cosine of 5 pi. That's using our whole, too bad we just did this one, but that's okay. There's 2 ways you could do this, actually probably 3 ways. One way, could you just keep going around the circle until you figure out where 5 pi is? Right, just keep making the circle around. Works every time. Another thing to do is find the angle that goes with it, which means if you want, could you just keep subtracting 2 pi until you got an angle that you know from your unit circle? Or maybe you just know where 5 pi is because we just kind of talked about it. But just remember that if this is bigger than 2 pi, you can subtract 2 pi, and what do you get? 3 pi. Oh my gosh, that's still bigger than 2 pi. What could I do? Some people say, well, I can see right away I could subtract 4 pi, and I would get the answer. That works too. So just so you know, then I could take 3 pi minus 2 pi, and the cosine of 5 pi is going to be the same as the cosine of pi. That's what I mean by being periodic. It's another way of saying coterminal angles. You don't have to show this work. If you know where it is, just tell me what the cosine of 5 pi is. It's the same as pi. So I'm looking for that ordered pair over there on the negative side, which is -1, 0. Cosine is the x, so the answer is -1. Definitely would be a no calculator question if I gave you something like that. Questions about that? And again, you're going to see some of those on your homework today. And then my last one here is, what if I said find the sine of -3 pi halves? And again, I want to give you two options here of how to do this. One is using what we've been doing. If I see a negative angle and I don't want it to be negative, what could I do to find the exact same spot on the circle but make it positive? Like over here, what did I do over here? I kept subtracting 2 pi because this one was bigger than 2 pi. Since this one's negative, could I add 2 pi to figure out where that same positive angle would be and then use that angle? Always works, every time. What else could I do that we learned today? We could use the even and odd function thing. Is sine even or is sine odd? Which means I could say that the sine of -3 pi halves is the same as the negative sine of 3 pi halves, right? If you go back and look how we wrote that out, if you have the sine of a negative angle, it's equal to the negative of the positive angle. And that's how you can use those even and odd functions. Do you know what the sine of 3 pi halves is? That's what you see on my paper a lot. I draw a little picture, and I say, where's 3 pi halves? Down here, right? What's the ordered pair down there? 0, -1. And sine is the x or the y? So the y is -1. So this is like saying negative of -1. Or the answer is just positive. Just so you know, you don't have to use that. You could have just added 2 pi here. And if I take -1.5 and I add 2 to it, that's the same as the sine of pi halves. Is the sine of pi halves equal to 1? I get the same answer. So that's why I'm saying there's lots of options here that you can use when you're doing these problems. But I just want you to be aware of how you could evaluate them. Unit circle is really great for these points here. The ones in the middle, you either need to learn the unit circle or you need to be able to draw those 30, 60, 90, 45, 45, 90 triangles in the right spots. This is it. This is the last new stuff before we're going to have a test. Which means I think we just need to finish the homework. Like day 3, you were supposed to do 29, 31, and 67 through 70. If you haven't done that, you need to finish it. But I believe this would be, we could call this day 3 part B, or we could just call this 4-3 day 4. On your homework sheet, it's only listed as 3 days, so it's kind of a bit confusing. But you need to finish this up today. 37 through 42, and then 49 and 50. And lots of them, they don't have a lot of work to show with them. It's just using the fact that you can add and subtract 2 pi. If you still have other questions on old homework, it'd be a great time to ask. Otherwise, you can get started on this in case you have a question. The plan is we're going to do a worksheet tomorrow, kind of summarizing this, but also going back to some of the 4-1-4-2. So it's kind of like a review worksheet for the test. But then Friday, we'll review also like what's going to be on the test, what's going to be on the no calculator part versus the calculator part. And then Monday, you're going to take that first part of the test, which will probably be the no calculator part first.